recently, major advance recently in the proof of the fields conjectures, which go back to 2018 and the introduction of the delta conjecture. And Andy Wilson's going to tell us all about it. So go ahead, Andy.
Thanks very much, and thanks to Anna and Jim for the invitation and for organizing this series. Um, so let's see, this is joint work with lots of people who you can see here. You're going to hear from Brendan later in the summer about several aspects of this. Uh, I guess before I get started, my plan is to give just a few slides at the beginning here to kind of introduce you to the overall idea of what we're going to talk about, and then I'll switch to taking notes when I want to get a bit more granular. And you should feel free to stop me at any time. I'm not monitoring the chat, but you should interrupt me if you have any questions. Okay, so the story starts here with the classical covariance. So we've got the polynomials and n variables, which I'll just call S. There's an action of the symmetric group Sn, well, mathfrak Sn on these that acts on the indices. And then there's the ideal of invariance I. So these are the invariants of no constant term, right? So the things that don't change under any of the permutations. And if you've seen symmetric functions before, you know that you can write this ideal as being generated by either the power sums or the elementaries or the homogeneous symmetric functions. Um, I'll probably mostly look at elementaries in this series, but there are lots of ways to think about this ideal. And we form the classical covariant ring, uh, which I'll call R, and it has the structure of a graded SN module. So we can think of terms that are homogeneous of each degree. The SN action doesn't change the degree of anything, so we can look specifically at that piece. You get another SN module, and it breaks up that way. Um, so this is a slide that's meant to capture kind of some selected results about this quotient ring, specifically the ones that we will need in our series. You could this slide could have 10 times as much on it, and then you couldn't read anything, right? But this is what we'll need or what we'll need most. So kind of starting from the top is let's see, starting from the top and going down, the dimension of this as a vector space is n factorial. And if you want more information, you could ask, okay, what's its SN module structure? And that's this result of Shibali that it's the same as the regular representation of the symmetric group. You could ask something like, okay, what about that graded SN, graded vector space structure? Well, you get roughly the Q analog, well, you get exactly the Q analog of n factorial there for the Hilbert series. Going down, you can ask for even more detail. Maybe you want a basis. One such basis is given by Artin, this staircase basis. So the exponent vector kind of lies under this staircase here. Or over here, the kind of most possible information you could ask for in some sense is what is the graded SN module structure? And it turns out that where it is, the irreducible V lambda appear, it appears in Ri equal to the number of standard Young tableau of that shape lambda with major index I. So this is a unpublished result of Lustig and Stanley. What is reference for Shivali? I don't know it off the top of my head, but I can dig it up for you. Um, Yeah, if you remind me, thanks. Sometime in the 50s or 60s.
The paper has complex reflection groups in the title. I
Thank
remember
you.
that. The invariance of complex reflection groups, I think. He uses the normal basis theorem actually to prove that from Galois theory.
Thank you, Brendan. Yeah, you should refer all your detailed questions to Brendan, because he's not speaking yet, right? Um, okay, so I figured I would just give an example of what this looks like when n equals 3. I know that Jim and Anna like to kind of lead with examples in this series. So, okay, when n equals 3, the dimension is 3 factorial. Here's the Artin basis. As I've presented it, sometimes you might see these as the variable names kind of being flipped. And if you look at the degrees of the things in the Artin basis, you get the Hilbert series, and that is the Q analog of 3 factorial there. And if you want to know the graded SN structure, you look at the standard Young tableau of size 3 and compute their major index, and that tells you kind of what level the irreducibles show up in. Okay. So Um, what else can you say? You can look at other types. So you could look at any irreducible Weyl group of rank n. It acts by the reflection representation on a vector space, V, of n-dimensional vector space. So it acts on polynomials over that space or the symmetric space there, and you can form the co-invariant ring there. And it turns out that similar sorts of thing hold. Schiavelli's theorem still works. Uh, you know, um, this is one direction you can push things in. And I guess I'm not going to talk too much about kind of this sort of thing. Maybe Brendan will have some time at the end of the series to talk about kind of ongoing work, looking at type B and so on. But we haven't discussed that, so we'll see. Um, Another direction you could go in is look at what are called diagonal coinvariants. So you take several sets of variables. In this case, I've got k sets of variables. And you could have the symmetric group act on each of them simultaneously. So just one copy of the symmetric group, but acting on all of them at the same time, and quotient out by the invariance there. And historically, people are most interested in two sets of variables. This is the kind of shuffle conjecture now theorem story, right? So Mark-Heyman proved that the dimension of the space is n plus 1 of n minus 1, that its Sn structure is basically that of Sn acting on parking functions tensored with a sign. And this is related to things like the shuffle theorem. But results in this direction kind of dry up fairly quickly. There are a couple things known when k equals 3. John Lenfer has some recent work about, arbitrarily many sets of variables and what you can say there. But it gets hard very quickly. And this was mostly done in, well, I guess Heyman's work in the 90s and early 2000s, Carlson Mellett in about 10 years ago now. Okay, so the direction we're going to take is slightly different. I mean, the point of these last two slides is basically, you know, low-hanging fruit is no longer available in either of these directions, I would say, right? Or maybe even medium hanging fruit. So what is superspace? We're going to just take a copy of the exterior algebra in rank n and n variables here and tensor it with the polynomial ring, and I'll call this capital omega. Um, so if you like to think in terms of coordinates or variables, we have x variables which commute with each other. We have x and theta variables which commute with each other, and we have theta variables which anti-commute. In particular, they square to zero. Um, and Sn still acts on this thing kind of simultaneously or diagonally, you might say. And we can form an invariant ideal. It's a result of Solomon that you can just take any old generating set you like for the polynomial invariance and then apply this Euler operator d to each of them. So here's the definition of that operator. It's maybe familiar from multivariable calculus, working with one forms and things like this. Um, and you kind of append that to your original set of generators, and you get a set of generators for the invariant ideal of superspace. Um, okay, we can take the quotient, play the same game. Now we have two gradings, right? Because there's an x grading and a theta grading. How many x variables do you use and how many theta variables do you use? So I'll break that up this way. It'll often be helpful for us to kind of fix an overall theta grading and let the x grading vary. So that's what this notation means. Um, so what can we say about this thing? Or maybe before I go in that direction, why should we try? Well, you can think of these as polynomial value differential forms if your thetas are, your dxi's from calculus. It has some roles in mathematical physics where we can think of x's and thetas as bosons and fermions. Particularly the thetas squaring to zero is like, two fermions can't share the same state, et cetera, right? Um, you might hope it's easier than diagonal covariance, even just for the naive reason that there's only finitely many monomials in the thetas instead of infinitely many monomials in a polynomial ring. Um, and I guess the it ends up being true. I'd say this is, easier than some of Heyman's work. In particular, we don't have to invoke anything about um, about kind of heavy algebraic geometry, right? Uh, the reason this originally came up is related to the delta theorem, which I'm not going to talk about in detail, but again, maybe will come up at the end. This was actually when there's two sets of polynomial variables and one set of exterior variables. This is related to the delta theorem. This was a conjecture by Mike Zabraki. And I mean, hopefully I'll try to convince you it's just fun to think about. So thinking about this space involves thinking about ordered set partitions is one of the main morals of this. Um, so what do I mean by an ordered set partition? Well, you just take a set partition and you order its blocks or parts, right? So here I've written down all the ordered set partitions of three things. They include all the permutations because you can just put each element in its own block, but you can also group some of them together, maybe two together and one separate, or you can put them all in one block. So there's 13 here. Um, and if you like thinking about this more geometrically, these are nice in bijection with codimension k faces in the Coxeter complex for the symmetric group. So you might think of, this ray here where x1 and x2 are equal and are less than x3 as corresponding to this ordered set partition, where the first block has 1 and 2 in it and the next block has 3. And then we also have, of course, the regions and then the origin where everything's equal. So the kind of first thing we can prove, this is just a basic combinatorial statement about ordered set partitions, is there's this many of them. So this is very believable. You take a set partition of which there are Stirling number of the second kind many, and then you permute its blocks in k factorial ways. This equation is maybe slightly takes a second to believe. Um, you can think of this as the analog of, the size of Sn being 1 times 2 times 3 up to n. Here we've got these what we call lazy staircases. So they start at 1, they end at some value k, and they go up by either 0 or 1 at each step. Um, so I've kind of drawn a little tree here to try to give you some sense of what this looks like for this lazy staircase. Um, you can think of this as like an insertion type situation where, okay, if you start with 1, you've got two choices of where to put 2 into a new block. But if this staircase kind of tells you, okay, it doesn't go up, so 3 should go into an existing block. And then there's two choices for that, right? Um, so this 2 also tells you put 4 into an existing block, so there's two choices for that. One second here. Okay. Um, any, well, I'll just keep trucking along. Let's see. It looks like there's something in the chat. Oh, it's just a thank you from earlier. Okay. Um, So the moral of the story here is that ordered set partitions kind of govern the superspace covariance in the way that permutations govern the usual invariants, covariance rather. Um, so we have this series of conjectures by this group from Toronto that kind of they made around 7 years ago now. Um, So the conjectures are that the dimension of this thing is the number of ordered set partitions, and that the way that it looks like as an SN module is the SN acting on ordered set partitions up to this sign factor. Um, if you want the graded vector space information, you get kind of Q analogs of these lazy staircase products. If you want a basis, this should really be attributed to Bruce Sagan and Josh Swanson. But roughly, you get kind of an art and style basis where the thetas tell you where your staircase is lazy, and the x's choose some vector under the staircase. Um, and then there's some statement down here about standard Young tableau, which uh, hard to parse in real time, maybe, but it's not too bad. Um, And these are all true. This is the main result of this series. So these were solved in a series of three papers. The first one came out 3 years ago now with Brendan and I, where we proved the Hilbert series is what it stated there. And then after that, Brendan and these other authors use some hyperplane arrangement techniques to prove that the basis is what we thought it was, or a basis is what we thought it was. And then finally, last year, Satoshi Mirai, Brendan, and I proved the graded vector space, the graded SN module structure. Um, okay, so before I get into that, again, trying to write down examples. So here, this is SR11 when n equals 3. So we want x degree 1 and theta degree 1. So that means there's one kind of lazy step, and the theta marks that lazy step. And then you take any kind of vector under that lazy staircase, and that gives you your x degrees in a basis. So this is a three-dimensional space. Um, and if you care about the graded SN module structure, you again write down all the standard Young-Tableau of size 3. Um, you take some kind of generating function and you try to pick out the terms of q to the 1 and z to the 1. It turns out that it's these two irreducible representations there. Okay. Um,
And Lee, can you walk us through how you decide how to draw the lazy steps
oh yeah,
and like
sure.
how to
So n equals 3 means there should be three steps. It's a little bit confusing because these are both 1, but the second factor, the theta degree here, tells you how many lazy steps to make. Um, in that case, so your possible staircases look like this or like this, right? These two. And then you kind of draw some dots under the staircase and count how many blocks under the dots. That's what I'm trying to picture here. So it turns out this staircase yields two different basis elements because there's two different ways to choose a exponent vector for the x's underneath that lazy staircase. You can um, of total x degree 1 is what I'm shooting for here. There's others, right? But they give you different x degrees. Um, And then this guy has only one possible x degree 1 thing. Does that make sense? Um,
By the way,
it is indeed raining and thundering here, so I'm trying to keep my dog under control at the same time as this. But yeah, Jim, go ahead,
I just had a thought, a little bit off center,
please.
but is there a possibility that for the whole delta thing, where you have the extra t parameter, that a Schur coefficient could be written as a sum of products? Because I know the monomial expansion can be written that way.
I don't know. It is possible. I'd have to think about it more.
All right.
Um, any other questions or comments? Now is a good time. Okay. So what's the plan then? This is the end of my slides in a minute here. So my plan is to actually try to sketch out the proof of all of these, or the resolution of all of these conjectures, not just the most recent paper. I mean, have to sacrifice some detail to do that, but I feel like just picking out the last paper would not really give you an understanding of what's happening. Um, so my plan is to give 2 to 3 lectures along these lines. So the first thing will be to do some kind of leading term analysis to decompose this into polynomial quotients again. So we'll kind of turn this back into a problem about polynomials from one about superspace. And then we're going to look at these resulting ideals, maybe switching the order of these two things depending on timing, but basically show that these resulting ideals are nice using some commutative algebra and use some theory of hyperplane arrangements to give you some sense of why this decomposition is correct. And then I'll let Brendan take over. He'll show you all sorts of nice things about the Vandermonde and harmonics and bases and so on. So really at the end of this series, end of my talks, we'll only get to about this thing. And in fact, we'll only get one direction of this equality. We'll get, I think, this one. Um, so it doesn't, you might say that's not enough, right? For 2 or 3 lectures, but I'm hoping that we'll lay enough kind of groundwork that the going will be a little bit easier for Brendan when he takes over and talks about the basis and also about how to bound this in the other direction, this bottom area. Okay. Any questions for now? Okay, so if not, I'll move over to writing some notes. And so I'll talk about leading terms in a minute, but the real thing I kind of our goal here is this to write this Hilbert series. Uh, like this product of these lazy staircases. Or Q analogs kind of from lazy staircases, where each difference is either 0 or 1. And these are Q analogs. And as I said, I'm probably only going to get, one direction of this equality in the next couple of talks. But the main kind of first thing to do is to turn this into a problem of polynomials again, somehow like or rather several problems about polynomial rings. So I can finally, given the extra time available to me in this series, kind of uh, answer a question I often get when I talk about this, which is, what about Grobner theory? People have paid attention correctly in their applied algebra classes or whatever. They learn that Grobner bases solve a lot of your problems for you, right? Why don't you just find a Grobner basis for this and surely you're done, right? And there is the Grobner theory for superspace. That's maybe not something you cover in your first class, but there is such a theory built up. And the answer is we can't say what the Grosvenor bases look like. We can't pick a nice monomial ordering that makes them look nice. Um, does that mean it can't be done? Probably not. I spoke to Mike Zabraki and Francois Bergeron about this once, and I think they had said they had done some actual tests, basically like pick all monomial orderings and show that, well, all the Grosvenor bases you get out are, messy. Again, what does messy mean? It's in the eye of the, basically they eyeballed all possible Grosvenor bases and they couldn't say anything about any of them, right? So we'll have to take a different approach, but we will kind of morally at the beginning here at least try to use some ideas from Grosvenor theory. I'll call this kind of leading term theory instead of Grosvenor theory. So what do I mean? I'm gonna pick an order on monomials, theta monomials. So let theta be. Um, what about Allen style non-monomial orders? Um, yeah, so this is it's not clear to me what exactly what all, trying all orderings means if they included things like this or not. I guess I'll just say that we've tried a lot of things. Have we tried this? We tried like weighted orderings, right? Where you can put various weights on things and they haven't worked. I'm not sure
I'm
if that includes this, but go
I'm
ahead.
not sure. I mean, sort of the classical story here is this is how you get the Steinberg-Garcia-Stanton monomials. And there's a version of this that works for R and K. You get kind of very similar monomials multiplied by e's, basically. But I think at some point I thought about this, but I wasn't able to make it work in this context.
Mhm.
I mean, the hope in some sense is that you're not using a monomial order. So you're kind of getting out of this world where everything's messy, but you know, uh, no success so far. But good question, Dari.
It has been a few years since at least I've tried this, so hard to remember what I did and didn't try, but
And I should say that it is an open problem to get a descent monomial basis for the superspace covariant ring. So That might be kind of an interesting thing to think about either way.
That's right. Yeah. So, I mean, going back to my initial slide about there's lots of things I left off that are known about the classical covariants that I didn't put on there, and that's pretty much because we don't know about them in this case. So, other bases, Schubert bases, things like this, we don't know really. So there's lots to explore there. Um, okay, so I'm going to take an order, but just on the theta monomials. So this is the Lex order on monomials of the exterior algebra. Sometimes the Gale order is another word for this. And um, I'll write these monomials in kind of a shorthand where this is um, the wedge product or the product of a bunch of elements in a set. Let's say it's increasing order. Okay, I'll define the leading set. I'll call this LS of F. So this is the maximum set. Oh, sorry, I skipped something. Then we can write any F, any superspace element F as um, summing over these sets J. So where this is the polynomial, right? Um, so we'll take a leading set. The first non-zero polynomial here. And if the leading set is some set K, then we'll write down the leading coefficient of F to be this polynomial coefficient. So I'm not taking an order on all of superspace, but just on the exterior part, right? And then for any ideal I in superspace and subset J, we can look at the J initial ideal. I'll call it In sub J of I. This is the polynomial ideal generated by all of the leading coefficients of things in the ideal with a specific leading set. I'll say a little bit more precisely about this in a second. And this is indeed a polynomial ideal. And we have this lemma, which I won't prove. You should think of this as kind of like doing the job of Grobner theory, though. It says that for any homogeneous ideal, I'll call it I guess. Okay, I'll go with lowercase a. My math frac lowercase a is not up to par, but so we can look at the dimension of superspace mod this ideal. Say we want it's homogeneous, so there's an x graded component and a theta graded component. Basically, you can get this particular dimension by looking at all the subsets of size k and the dimension of all these initial ideals, specifically the ith graded piece of them. Okay. So if you want to understand the dimension of this superspace quotient, you could try to get there by understanding the dimensions of all, n choose k of these initial ideals, or rather their quotients. Okay. I'll write down an example in a second. But this is what I mean when I say we're trying to kind of transport this problem back into the polynomial world, right? So our claim, which will again take a while to prove, is that these initial ideals for our particular superspace ideal are nice. So if one is an element of the set, then the initial ideal is just so this is SI, I mean this the superspace invariance. This is just the whole thing. And if one is not in the set J, um, well, there's a few ways to write this down. We're going to kind of use different options at different points in this series. Um, the first thing I'm going to write down is actually something which is not in any of the papers. It's something we discovered later, talking with like Sean Griffin, among other people, but haven't had a chance to use it in any real ways. But to me, this is kind of the friendliest way to write this thing down, um, because at the beginning it looks a lot like um, something we're familiar with, um, a bunch of elementaries, but not well, all of them are actually in here. But anyway, and then there's some other generators which are a little bit stranger. They look like this. So it's the product of I less than little j, I not in the set, um, these linear forms. And this is for all elements of the set. Um, so I don't know, what does this make you think of? It makes you think of van der Waals determinants, makes you think of maybe Hessenberg variety cohomology if you've read about that before. It's not exactly any of those things, but it's, of a similar flavor. Um, so let me try to write down some example. Um, Maybe I'll try to have a running example of something like n equals 5. J is the set 3 comma 5. Then the initial ideal here would be, well, the first three elementaries, because that's 3 is 5 minus the size of j, which is 2, plus what are these other generators? Well, we get this coming from the little j being 3, and from little j being 5, we get this. Okay. Um, and one thing you might notice is if we look at the degrees of these things, right, we have degree 1, degree 2, degree 3, degree 2, and degree 3. This is exactly the kind of lazy staircase of that doesn't increase in positions 3 or 5, right? Um, that's no accident. Um, and I guess maybe I'll say one more thing about this leading term theory. So it's actually not hard to take care of this case where one is in your set. Right? So if one is in your set, um, well, we've got elements. Well, this particular element is in your superspace invariant, and I can just multiply this by something like this. Is that what I want? Yeah. So this is definitely in SI, and its uh, leading set is capital J with leading term 1. So this says that 1 is in my initial ideal, and that's what kind of the first part of this claim. Roughly, if 1 is in your set, it's not hard to see you get this ideal being the whole thing. What about other sets? And that's going to be kind of the content of most of the rest of this series. Um, any questions so far? Okay. So there's kind of two prongs of what to do next. I can try to convince you of this equality. I think I will hold off on that for now. Instead, what I'll do is actually just kind of look at these ideals over here and try to convince you that they are what we want them to be. And I'll try to tell you what that means. So we have this polynomial ideal with some elementary symmetric functions in it, and then these products of linear forms, xi minus xj. Um, why is that good, right? If this equality is true, right? Well, we're going to use some tools from commutative algebra, which I'm going to kind of smash together into this lemma here. Um, the lemma goes like this. Let's say I've got a sequence of homogeneous polynomials of positive degree. If this polynomial system, where I want them all to be equal to 0, has only the trivial solution of all zeros, and I mean working over C, this is like the only time that's important, at least for now, then what do we know? Then we know something about the dimension of the quotient space. We get that it's Hilbert series. Um, oh, yeah, in there somewhere. Um, maybe there. Is the products of the Q analogs of the degrees of the Fs. Okay. And I'll give you some example of this in a second. So I'm kind of smashing together a bunch of things from commutative algebra or kind of classical algebraic geometry. Um, such a sequence is called a regular sequence, usually not defined this way, but hopefully this will be good enough for our purposes. So how to think about this statement, if this is not something you're familiar with. Um, well, I mean, okay, I'll start with a couple very kind of well, one very basic example and then one less basic example. Um, so what if we just have two variables and we look at the quotient of the ideal generated by, I don't know, a single power of x and a single power of y, right? Well, these have nothing to do with each other. So the linear dimension of the quotient is just we'll take any x power from 0 to a minus 1, take any y power from 0 to b minus 1. Um, you can, uh, this is kind of classic commutative algebra in the plane, you might say, I guess. But the product of the degrees of x to the a and y to the b. But of course, this doesn't always happen, right? If this were, x to the a and x to the b, well, it's not a times b anymore. It's, the minimum of a and b, right? So, in some sense, what this is capturing is that the f's are, generic. They have very little to do with each other, and if that's the case, then the quotient space has kind of the expected dimension, right? Um, So let's do another kind of example application of this. Um, What about back to n variables? Um, what if we let f sub I be, um, the elementary symmetric function e sub I? Um, well, if, say, I evaluate E1 up to En on some point Z and I get all zeros, uh, does that mean that Z is the zeros vector? It does. Um, One way to see this is maybe with kind of Galois theory, right? So if the Z's are your list of roots, um, then we know that the E's tell you, various coefficients in some polynomial, right? So like right in the Z's, right? And if all these are zero, then our polynomial in this additional variable t is just t to the n, and we know the roots of that are just all zeros. So your point z must be all zero point. So the elementary symmetric functions have this nice generic property of being a regular sequence, right? Um, okay. So what does this have to do with what I was speaking about earlier? Well, the generating set I wrote down earlier also has this property. So if one is not an element of our set, then the only common zero in the complex numbers of, well, we've got these E1 up to E sub n minus capital J. And then we've also got these other types of generators. One for each element of the set. This only has the trivial solution. And then if we believe this for a second, right, then that means that the dimension of the associated quotient space is the product of that staircase that we saw earlier, right? Because that's the degrees of these guys. Um, so that would give us what we wanted kind of on the dimension side, right? Um, I'll try to sketch the proof of this in my last time, but are there any questions now? Okay. So this is um, I this is not also not written down anywhere because these generators kind of showed up after we did all this work. I talked a little bit about this with one of my colleagues, C. Chan, who's in number theory. But I figured maybe there's some Galois theory that could help us here. But really, the proof that he suggested to me is quite kind of uh, in the realm of generating functionality. So it's really quite nice. The idea is, well, if you have some common zero, um, you can actually maybe suppose that none of these entries are zero, but let's not worry about that too much. It is a proof sketch, right? You look at the generating function for the elementary symmetric functions. We know it looks like this. But we also know that a bunch of these terms are zero because, well, E1 is zero, E2 is zero, all the way up to E sub n minus psi sub j. So I can just eliminate those from my sum. This goes from n minus size of j plus 1 up to n. Okay, so a bunch of those terms vanish, right? So we're not quite as lucky as in the previous case when like everything vanished, right? Uh, in this case, but we've got a polynomial with a bunch of zero coefficients after the initial constant term of one, right? Um, and we also know something else, which is that we know that these products vanish. And if you think about this for a minute, what this tells you is that each z sub little j appears earlier in the list, right? Either it's equal to z1 or z2 or z3. That makes one of these zero. The only maybe kind of concerning thing is, what if it's equal to some previous element from the set? Well, that thing appears even earlier in the list, right? Because of this condition. So this tells us that each z sub j appears in one of the earlier entries. Okay. So you can think of it as you've got a polynomial with a bunch of zero coefficients in a row, and then some bound or some control on how many different roots it has, how many distinct roots. Um, if you like thinking about this kind of from a number theory perspective, maybe that's Galois theory-ish perspective. Um, okay, so then we can factor E sub t as a product just over the I that aren't in the set, because these are the only possibly unique roots, right? Um, so each a sub I is at least one. Basically, these repeated roots, we're just going to group them up with the roots that showed up earlier in our list. Um, so we have these two expressions for the same thing. And now this is maybe where my sketch will get a little bit even sketchier, but basically it's generating functionality. You can take logs and comparing coefficients. We get something like this. Um, we get some system. You look at the coefficient of t to the 1, which you know to be 0, and t to the 2, which you know to be 0, and so on. Um, so this is for k equals 1, 2, n minus psi sub j. And this is a Vandermonde system, right? We have all these iterated powers of these z's. So you have a Vandermonde in the z's times some vector, a vector. And if that's 0, well, you know that the Vandermonde is non-singular. So the only way that can happen is if these a's are 0, but you know that they're not 0 because of the way that they were selected. So roughly this implies well, how do you finish this? There's a couple of ways, but you can kind of use this to like kind of eliminate one of the roots and go down in degree. Um, um, so maybe I'll consider that the end of my proof sketch, but happy to chat about this more if this is something people are interested in, or I'll just try to finish with something else. Oh, maybe this is a good time to say that I am trying to write some notes about this. Uh, if I get them to a presentable form, I can send them to Anna, and you can look back on them if you're curious.
Sure.
And I can also send the handwritten notes. Okay. So I'm just about out of time for today. Maybe I'll just give a couple ideas about what I'm going to do next. Um, So this suggests then that,
Yes, small question.
yes, please.
What did you use the fact that one is not in J?
Let's see, where did I use that fact? I might not have.
Well, if one,
Yeah,
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 you would have the empty product appearing, which is one.
Oh, okay.
that's
So
right.
the
Yeah,
one is in say you get the unit ideal, which is in our context not really so
Oh,
interesting. So,
yeah,
so
thank
we're
you.
really kind of focusing on the case where one is not in J and one.
that's right. It's not that it trips up the argument, it just becomes kind of a notational annoyance or something. But yeah,
Yeah, and there's also this business where it's kind of a convention in commutative algebra. Regular sequences have to have positive degree. It's like you can't have one in a regular sequence, but the unit ideal is not so
Yeah.
scary.
although like I suppose that is it's this statement is still
Yeah,
true.
yeah, yeah, so that's true. It would have
Degree
not
zero.
a
Yeah,
trivial,
yeah.
so it would have no solution. So that's yeah, yeah.
Thank you. Any other questions? Okay, so just to finish up then, let me say that these ideals basically have the right size to do what we want, which is give us the Hilbert series, but are they actually equal? I claim that they're the initial ideals I discussed earlier. I mean, if they're not, then what are we doing here, right? So I'll say a couple of things in that direction. First, I want to say I'll kind of maybe start next time by presenting these same ideals as colon ideals, and we'll use some orbit harmonics to do this. And we won't use this right away, but I think this will make Brendan's job a little bit easier later, so I'm going to do it while I'm kind of on the topic. And this is how we thought of the most of the project is as certain colon ideals. Um, and I can even kind of for those of you who are kind of comfortable with this idea, maybe I'll even write down what I mean. So it's going to be this ideal. So it's everything that when you multiply it by that factor lands in the classical covariant ideal. Turns out this is the same thing. I'll try to convince you of that at the beginning of next time. And what I'm really going to do next time is use hyperplane arrangements, specifically Solomon-Tarot um theory, to to argue that these are related to the actual initial ideals. And again, I'm not going to get an exact equality, but I'll get one direction. So we'll see a couple techniques from orbit harmonics, from hyperplane arrangements. One thing I really like about this project is it really does require you to kind of grab techniques from all over. But yeah, we'll see some of that next time. Um, I think I'll stop for today. Any questions? Other questions? Another advantage of this is that if uh, the approaches will be quite different each lecture. So if one isn't to your taste, the next one might be more so, right? Hopefully.
I wanted to mention that if you haven't seen these lectures before, Anna and I will have the video posted on the IPAC seminar webpage. So, of course, everyone's seen this, but if you know anyone who missed it or whatever, they can view this lecture.
Yeah, I'll
Yeah.
send Anna some like
Yeah.
PDFs and stuff too.
All right. Well, let's thank Andy. You're
Thank you
good.
all.
And really looking forward to Thursday's lecture and more on these beautiful ideals. Okay, so see you later, everybody.
Thanks, everybody.